Hi guys, thanks for tuning into my video. Over the past couple of weeks we've done a lot of talking about vectors, parametric lines in 3 dimensions, projection, and one quick topic that I thought I might talk about is how if you've ever seen any kind of art out in the real world called anamorphic art, that kind of artwork is actually completely related to the topics that we've been talking about in class. So if you've ever seen really neat sidewalk art images, this is an example right here. This would be called an anamorphic illusion. And the way it works is this image, in reality, everybody else who's kind of standing around this sidewalk area sees a distorted looking image. But if you look at this image from just the right vantage point, it looks like a really convincing illusion. And the idea here is what you've done is you've projected a 3-dimensional image onto a flat 2-dimensional plane, and from just the right vantage point you're going to get what looks like a really convincing 3-dimensional image. There's a popular YouTube video that you might have seen related to this topic. Let's check it out. So you can see this video's got about 27 million views. It went viral a couple of years ago. Let's watch just a couple seconds of it. Whoa! Alright, so in this video you can see the basic idea is the combination of an optical illusion and also some good lighting, some high quality cameras, some dramatic music. You can make a really stunning video. But the idea here is it looked like there was a 3D image, in this case a Rubik's Cube, sitting on the table. And in reality it was a projection of that 3-dimensional Rubik's Cube onto the plane z = 0, onto the xy plane essentially. And it's really convincing if you're looking at that illusion from the correct vantage point. And we can actually do the mathematics behind it, and that's kind of the neat thing. So here's the idea. Let's say that we have a vantage point, a point in space that we're viewing from, we'll say ABC, this blue point right here. And then we have the object that we want to project onto the plane z = 0, onto the xy plane. In this case, I'm just going to project a single point. I'm going to call that point DEF. It's this red point right here. Well, you guys know how to come up with the parametric equation of a line. So here it is. Connect a line between ABC and DEF. And beyond that, you guys know how to come up with the equation of that line. It's hidden here inside of our code if you look for it. I've got my vantage point A, B, C, plus t times the vector connecting those 2 points, DEF minus ABC. Now the idea for this anamorphic illusion is if you look at this image from the exact right vantage point, so if we're looking from point ABC at point DEF, if we do our projection here, we could basically continue this line until it hits the plane z = 0, until it hits the xy plane, and the point DEF and the point on the plane will be indistinguishable from that particular vantage point. And that's what we just did. I continued this line segment that began at ABC and then went through DEF. I'm going to continue it all the way until it hits the plane z = 0. Kind of like that. Well, you could think of that as solving an equation, right? I need to figure out when my L of t, my line connecting ABC and DEF, has a z coordinate of 0. And this is the equation that I've set up right here. I'm solving the equation the z component of L of t, the third component of L of t, is equal to 0, and I'm solving that equation for t. If you run the code there, you get that t is equal to c over c minus f. So that's the particular t value at which that parameterization of the line intersects the plane z equals 0, the xy plane. And you could take that a step further. You could take that t value of c over c minus f, and you could plug it into the equation for the line, and this is our projection. If you have a vantage point ABC, and you have a point DEF that you want to project onto that plane, this is your projection. You could see, as you'd expect, the z-coordinate is 0, and then we've got an x-coordinate of CD minus AF over C minus F, and CE minus BF over C minus F. Now there's some linear algebra that's going on in the background here that I'm not going to talk about at length, but if you take a linear algebra class in the future, you'll see some connections here to that topic and what we're talking about right now. And you might even kind of notice things that look like determinants in there. That's not an accident. That is happening, but we're not really going to talk about that too much. And then I could take this little manipulate here, and I could press this button, and you could see my projection of the point DEF onto the plane z equals 0 occurs at my L, my line, evaluated at a t value of c over c minus f. Now this projection is not particularly interesting, right? Starting at a particular vantage point and projecting a point onto a plane is not all that interesting. It doesn't make for a great illusion. However, what I can do here is I can take a surface. So I have a surface P of s comma t equals s comma 0 comma t, so a really simple parameterization of a surface. It's just a rectangle sitting on the xy plane. And I could use that projection that I came up with just a minute ago to project that every point on that surface onto the plane z equals 0, because every point on the surface is described by an s comma 0 comma t. So I can run that projection. Let's take a look first. So what I've done is I've taken my surface, and it's just a rectangle, and I put this image of a Rubik's Cube onto it. This is kind of my approximation of the actual three-dimensional Rubik's Cube. It's kind of like my three-dimensional Rubik's Cube sitting on top of the xy plane. And you'll see how that works in a second. But now to do my projection, you can see, I'm going to plot my original Rubik's Cube, which is a rectangle sitting on top of the xy plane. And then here's my projection of my Rubik's Cube. So for my D, I took the first coordinate of my P of st of my surface. For my E, for my y coordinate of the point I want to project onto the plane z equals 0, I took my surface P of st and took the second component, same thing for F, and then I ran it through that projection that we came up with together. And let's run the code and see what it looks like. And there it is. You could see that I have projected my quote-unquote three-dimensional Rubik's Cube onto the xy plane, onto the plane z equals 0. So you want to pretend this Rubik's Cube right here is an actual just three-dimensional Rubik's Cube that was sitting on a table, and I've projected it onto the plane, the xy plane, or the plane z equals 0. Now the idea behind this is that from a particular vantage point, from one point in space, if you were to look at the projection versus look at the actual Rubik's Cube, they would look indistinguishable to you. From every other vantage point, it looks off, right? Like the projection onto the plane is distorted, but from one particular point in space, in this case, I chose my ABC to be 0, negative 20, 10. So from that one single viewing point, from that one vantage point, you've got a really convincing illusion. The actual Rubik's Cube and the projection of the Rubik's Cube should be indistinguishable. And if you want to see that happen, it's kind of hard with the angles I've got right here, but I can run some more code where I'm just showing that projection from the correct viewing point. So I'm setting my viewing point to 0, negative 20, 10. I'm running the same projection I did before, and look right here, my viewpoint is this ABC. So I'm going to plot this projection, and I'm going to look at it from the point ABC. And even though this is a projection, it looks like my three-dimensional Rubik's Cube. When we're looking at it from this angle, it looks pretty darn convincing. Change the angle, and oh, it's distorted. I just did the same thing that was in that YouTube video, rotating, and you can see that it's actually distorted. So the mind is tricked right here, and then when we rotate, your mind is not tricked anymore. And finally, if you wanted to make one of these yourself, there was nothing special about my ABC. You could set any vantage point you wanted, depending on how you wanted your piece of artwork to work, how you wanted that to function. And then for the projection, we could do all of this in 2 dimensions. Remember that my projection was this x-coordinate, comma, this complicated y-coordinate, comma 0. Well, we don't need the comma 0. We don't need to be in 3 dimensions with depth. We could just take the x and y coordinates, and I could do a projection that just goes onto a piece of paper, and it's pretty much the same code. All I did was strip out the z coordinate instead of a parametric plot 3D, I'm doing a parametric plot, and let's run the code. And you could print this thing out on a piece of 8.5 by 11 paper, and cut it out, and glue it or tape it on there, and you've got yourself an anamorphic illusion that looks really convincing when you place your eye at the coordinates 0, -20, 10, where you get your units just by printing out on the paper. You can see how long a unit is supposed to be, based on how this ends up on a piece of paper. And just to show you that all of this works, so by the way, you could download this Mathematica notebook, and as long as you have a working copy of Mathematica at your fingertips, you could replace the image with something other than a Rubik's Cube, and you could replace this vantage point with anything that you'd like, and you can make your own anamorphic illusion. But let's just make sure this is convincing. So the first thing we need to do is cue up some dramatic music, and then we'll watch my version of the video, which, it's not as high quality, but it does the same illusion. So let's check it out. Alright, and there we go, anamorphic art. So feel free to download that Mathematica notebook, read through it, and look at that vector connection, make your own art. But I hope you enjoyed seeing a connection between what we were learning about vectors and things that exist out there in the art world. Okay, have a great day. Bye.